Hey guys, welcome back to the part 2 of our video. We will start right where we left off.
So, guys, today we will be discussing the engineering correlations ranging from friction factor correlations, heat transfer correlations, and mass transfer correlation.
तो
So,
बेसिकली काफ़ी सालों से काफ़ी साइंटिस्ट ने इन सब चीज़ों पे बहुत मेहनत करी है एंड दे हैव कम अप विद वेरियस फार्मूलाज विच वी कॉल एज एम्पिरिकल कोरिलेशंस एंड बिकॉज आई एम एन इंजीनियर आई विल लाइक टू कॉल देम एज इंजीनियरिंग कोरिलेशंस.
So, what kind of correlations have they developed?
so guys, next up on our agenda, as we have already discussed, we have friction factor. These are friction factor correlations. So, what do you mean by friction factor? Friction factor is a term basically given by also known as the Darcy friction factor, which is also called as the Darcy-Weisbach friction factor. This is denoted by FD. It's basically a dimensionless number that quantifies the resistance or pressure drop due to friction inside a pipe when fluid flows through it. It directly affects how much energy is lost due to a pipe's surface and flow characteristics. So, in case of laminar flow, this Reynolds number is less than 2100. Friction factor is basically FD is given by 64 upon Reynolds number. This equation is exact and it's derived from our beloved Navier-Stokes equation. It's applicable for steady state and incompressible. Also, this is applicable for fully developed flow in a circular pipe. And this equation is valid only when it's laminar, so Reynolds number must be less than 2100, as viscous forces dominate and the flow is smooth and orderly. This equation's advantages are basically that it's simple, accurate, and there are no assumptions or iterations for this. But this equation, as usual, has some drawbacks, like obviously this is not applicable for turbulent flow. It's not applicable for turbulent flow, neither it's applicable for the transition region. So basically, used for this equation is that it is used in microfluidic systems. Where the situation is such that the flow rates are very low, such as it can be used in, for example, our blood flow in capillaries or oil pipelines with high viscous liquids. Right. So next up, we have the equation for turbulent flow. So this formula is basically applicable for Reynolds number, which is greater than 4000. Now, this equation might seem a little scary because obviously we have to deal with disorderness. So this is given by 1 by root FD minus 2 log of base 10. Mind you guys, this is base 10 and not E. Epsilon upon D 3.7 plus 2.51 by Reynolds number square root of FD. So this equation seems very scary as it has introduced log. There are multiple factors. There is Reynolds number, there is epsilon, there is diameter. But this equation is completely empirical. So we have to not deal with any sort of pesky derivations or anything like that. So it's empirical and it's semi-theoretical. So semi-theoretical means that this is theoretically, analytically analyzed this equation, and we have found out that this equation is applicable for flow and it has been proved experimentally as well. And this accounts for surface roughness. Surface roughness is nothing but this epsilon which we have introduced. This is surface roughness. So this equation is widely accepted, and it is very accurate within transitional and turbulent regions. The first equation which was developed was known as the Dieters-Bolter equation, which was formulated in 1930s by Frank W. Dieters and LMK Bolter at the University of California, Berkeley. इस समय में क्या हो रहा था कि एक एफिशिएंट हीट एक्सचेंजर, बॉयलर्स और केमिकल रिएक्टर्स की डिमांड काफी ज्यादा बढ़ रही थी। बट उस टाइम पे लोगों के पास किसी भी टाइप का एक प्रैक्टिकल टूल नहीं था जिससे वो लोग एक्यूरेटली जो कन्वेक्टिव हीट ट्रांसफर कोएफिशिएंट होता है टर्बुलेंट फ्लो के केस में वो कैलकुलेट कर पाए। इससे बहुत ज्यादा लॉस होता था और बहुत दिक्कतें भी आती थी इंडस्ट्रीज में। इसलिए एक एक्सपेरिमेंटल डेटा को यूज करके एक जनरलाइज्ड फॉर्मूला इन्होंने डेवलप किया जिसे आज हम डिटर्स बोल्टर इक्वेशन के नाम से जानते हैं। This is basically an empirical correlation that balance simplicity and utility.
But Anushilan, will this formula be applicable everywhere?
So basically यार ये फॉर्मूला तब काम में नहीं आता जब प्रांडल नंबर बहुत ज्यादा होता है, और प्रांडल नंबर तब ज्यादा होता है जब हम एक लिक्विड मेटल्स के साथ डील कर रहे हो या जो पाइप की सरफेस वो काफी ज्यादा रफ हो। इसके लिए हमारे एक अलग साइंटिस्ट ने एक अलग से फॉर्मूला दिया है जिसको हम नीलिंस्की's इक्वेशन भी बोलते हैं। Now guys, we will deep dive into the heat transfer correlations. So correlations are basically important for designing heat exchangers, modeling pipe network, or just passing our exams. So first of all, we'll dive into the first one, which is fully developed constant wall temperature. So what this basically means is that in a pipe, the flow is fully developed. It is in a constant flow rate, and the wall temperatures are also constant. So in this case, what will happen is that the Nusselt number, we will take this as 3.66, and this is applicable universally regardless of what kind of pipe it is or what kind of fluid it is. If a fluid is fully developed and the walls have a constant temperature, then we will always use this correlation of Nusselt number being 3.66. This basically applies to long smooth pipes with steady laminar flow. So we will write this as this is applicable for long smooth pipes with steady laminar flow. And also this case is of that Nusselt number is always constant in this case. So this is basically used in water flowing through copper pipes with walls at fixed temperature. Now the second case we will talk about is fully developed constant wall heat flux. Now you might think that the constant wall heat flux and constant wall temperature, what is the difference in this? So the significant difference is that in the constant wall temperature, the temperature of the wall is same throughout the pipe, right? But in constant wall heat flux, the wall temperature increases along the length to maintain constant heat flux. As you might think that when water is flowing through a pipe, the temperature of the water may go down due to a temperature gradient. But in this case, the temperature gradually increases throughout the pipe so that the temperature of water also remains same. So, and in this case, Nusselt number is also constant and is taken to be 4.36. These two numbers are experimentally found out, analytically solved. So these are always constant, and we will write this as wall temperature increases along the length of pipe. So basically this process is used when electric resistance heating of fluid in industrial processes. In that case, Nusselt number is taken to be 4.36. Now our third case for heat transfer correlation will be thermally developing region. So this thing also has a name. Ark, can you guess what this equation might be called?
No, I don't know.
So this is known as the Griot's solution.
Oh, I think I have heard that.
Yes, sir. So basically now, this was constant, this was constant. Now things get real. This equation might seem kind of long and big at first, but it's not really that scary. So this is the 1.83 Reynolds number, Prandtl number to the power 1 by 3. So this formula is basically used in micro-channel heat sinks where short tubes are present in heat exchanger. And as Nusselt number drops along the pipe as the distance increases. And this case is now the thing is that Nusselt number here lies between the range of 3.66 to 4.36 downstream. And this formula is basically applicable when a fluid just about enters the pipe. At the entry region, this formula captures the heat transfer. This is not applicable throughout the pipe, just at the beginning of it. Like if this is a pipe fully developed and these two equations can be used along the length of the pipe, but this equation can only be used up until here at just the entry point. So these were all about our laminar flow. सो बेसिकली अब मैं आप लोगों को डीटस बोल्डर इक्वेशन के बारे में बताता हूँ। डीटस बोल्डर इक्वेशन बेसिकली इज नसल नंबर इज इक्वल टू 0.03 रेनॉल्ड्स नंबर टू द पावर 0.8 एंड प्रांडल नंबर टू द पावर n। नसल नंबर हमारा क्या होता है? बेसिकली इट इज द रेशियो ऑफ कन्वेक्टिव टू कंडक्टिव हीट ट्रांसफर। फिर रेनॉल्ड्स नंबर जैसे आपको ऑलरेडी अर्थ ने बता दिया है, वो बेसिकली फ्लो रेजिम को दिखाता है, जो कि हमारा इस केस में टर्बुलेंट फ्लो है। बट टर्बुलेंट फ्लो के केस में भी क्या होगा कि दिस विल बी बेसिकली एप्लीकेबल फॉर रेनॉल्ड्स नंबर विच इज ग्रेटर देन 10,000। एंड द लास्ट बट द नॉट लीस्ट इज प्रांडल नंबर विच इज द रेशियो ऑफ मोमेंटम डिफ्यूजिविटी to thermal diffusivity. प्रांडल नंबर को जो फॉर्मूला होता है वो बेसिकली म्यू सी पी बाई के भी होता है, वेयर के इज द थर्मल डिफ्यूजिविटी कोफिशिएंट एंड म्यू सी पी इज द मोमेंटम डिफ्यूजिविटी कोफिशिएंट। अब आप लोग ऑब्वियसली इस एन को लेकर थोड़े क्यूरियस होंगे कि ये एन क्यों लिखा है पावर में और एन की क्या वैल्यू है। तो एन बेसिकली क्या होता है? एन इज 0.4 जब हम फ्लूइड को हीट कर रहे हैं, और n को 0.3 लिया जाता है जब हम फ्लूइड को कूल करते हैं। ये सारे जो भी नंबर्स है एंड ये जो भी डेटा आया, ये सब एक्सपेरिमेंटल डेटा से आया है एंड देयर आर नो रियल डेरिवेशंस फॉर दिस, बट दिस इज कंप्लीटली एक्सपेरिमेंटल एंड एम्पिरिकल रिलेशंस। सो गाइस, नीलिंस्कीज इक्वेशन। अब आपको एक क्लियर कट कंपैरिजन दिख ही रहा है कि हमारा डीटस बोल्टर इतना छोटा सा है और हमारा नीलिंस्की इतना एक बड़ा सा इक्वेशन है, बिकॉज नीलिंस्की एक काफी रियल वर्ल्ड एप्लीकेशन पे बेस्ड है। यहाँ पे भी सिमिलरली आपको रेनॉल्ड्स नंबर दिख रहा है, नसल नंबर दिख रहा है और प्रांडल नंबर दिख रहा है, बट एक एक्स्ट्रा टर्म आ चुकी है, वो है ये एफ। सो ये एफ क्या है? एफ बेसिकली है हमारा फ्रिक्शन फैक्टर या डार्सीज फ्रिक्शन फैक्टर। अब आप लोग बोलेंगे कि ये फ्रिक्शन फैक्टर हम कहाँ से मिलेगा? सो फ्रिक्शन फैक्टर बेसिकली मूडी चार्ट, एक और साइंटिस्ट उन्होंने मूडी चार्ट बनाया है। बेसिकली वो दुनिया के हर पाइप के रफनेस को फैक्टर इन करती है एंड फ्लो रेजिस्टेंस को, ताकि पाइप में अगर कोरोजन या स्केलिंग की प्रॉब्लम आए तो उस चीज को भी हम अपनी इक्वेशन फैक्टर इन कर सके। सो दैट इज बेसिकली व्हाट फ्रिक्शन फैक्टर टेल्स अस। That's why Nielinski's equation is much more accurate compared to a Dietz-Boulder equation, and it has much more wider range of real life applications. Now, Nielinski's equation basically works for any range between 3000 to 10 to the power 6. एक्यूरेसी भी इसकी बहुत ज्यादा होती है बिकॉज ऑफ फ्रिक्शन फैक्टर, एंड ये ट्रांजिशनल फ्लो में भी काम कर सकता है। So now I have already told you about the Dietz-Boulder equation and the Nielinski's equation. But there is one more,
which is called as the Petukov's equation.
Wait. पेटोकोव्स इक्वेशन ना, आई थिंक इट्स सम काइंड ऑफ गोल्ड स्टैंडर्ड. बहुत सारी इंडस्ट्रीज में ये इक्वेशन यूज होता है ना, एम आई राइट?
Yes, sir, you're absolutely right. This Petukov equation is a modernized form of Dirichlet-Boulter or Nielinski's equation. This equation is basically used to design nuclear reactors. It is also used for cooling of hypersonic jets or in aerospace technology. So, Petukov equation was basically developed by Alexei Petukov in 1960s. This equation emerged from Soviet era advancements in thermal hydraulics. It became a gold standard, as you rightfully said, for high fidelity heat transfer modeling, particularly in aerospace and nuclear engineering. So, हम कह सकते हैं कि Petukov is like the Ferrari of heat transfer correlations. Precision engineering for smooth pipes and extreme conditions. While it demands more effort than Dirichlet-Boulter, its accuracy justifies its use in life or death application. Like obviously, nuclear reactor को मेल्टडाउन से बचाना है तो हमारा इक्वेशन जितना एक्यूरेट हो सके उतना बेटर इन ऑर्डर टू ऑब्वियसली अवॉइड रियल लाइफ डिजास्टर्स. और अगर Dirichlet-Boulter यूज करते रह गए तब तो कुछ नहीं होने वाला. सो बेसिकली अगर एक कंपैरिजन दूं तो Dirichlet-Boulter एक साइकिल की तरह है. नीलिंस्कीज इक्वेशन वहीं पे एक नॉर्मल डे टू डे गाड़ी की तरह है, बट पेटुकोव्स इक्वेशन एक एब्सोल्यूट फार्मूला 1 कार की तरह है, विच इज बिल्ड फॉर स्पीड, प्रिसिशन एंड हाई स्टेक्स रेसेस.
You can see that this is the Petukov's equation. This is very similar to Nielinski's equation as you can clearly see, but obviously there are some differences. Like, first of all is to calculate apply Petukov's equation. Firstly, we need to calculate F, which is the Darcy's friction factor. Now, there is a very particular formula in this, which is 0.079 into Reynolds number to the power minus 0.25. This formula is used to calculate the Darcy's friction factor rather than directly taking it from the Moody's chart. Now, Cedar-Tate and Dirichlet-Boulter might seem like quite same equations because they kind of are, but there are some slight changes. Because Cedar-Tate is considered to be more accurate compared to Dirichlet-Boulter due to just one factor. Because as you can see, here there is a constant, here is a constant. Reynolds number is used here as well. Prandtl number is also used. But the main difference between these two numbers are that we introduce a viscosity correction factor. This has become a game changer for this equation because this term alone makes this equation much more accurate compared to our Dirichlet-Boulter equation. These equations is basically used for food processing or crude oil heat exchangers. Now we will go over to our next equations, which is laminar flow over flat plate. Let's move on to our final topic, that's mass transfer correlations. As you already know, we have already talked about friction factor correlation and heat transfer correlation. And you have already seen that we have dealt with Reynolds number, Prandtl number, Nusselt number. But now there are two more dimensional numbers which I will introduce you into this part, which are basically the two pillars of mass transfer. One is known as the Sherwood number. Which is given by SH. So, Sherwood number is basically nothing but Kc into L upon DAB. Here, Kc is the mass transfer coefficient, L is the characteristic length, and DAB, as you might have already guessed, is the diffusion coefficient. So Sherwood number is very similar to Nusselt number, as Sherwood number tells us that how convection is more dominant over molecular diffusion. This part is convection and this part is diffusion. So Sherwood number, if it's nearly equal to 2, that would mean that there is very low convection and it's mostly diffusion. Now And if Sherwood number is very larger than 1, then convection is dominating. As you might have already guessed, this number is very similar to, as I have already told, the Nusselt number, which is given by HL by K. Nusselt number compares the convection. So this is HL by K. As you can already see that this is the convection part and this is the conductive part. So as Nusselt number compares the convective heat transfer to conductive heat transfer, here Sherwood number compares the convective mass transfer to conductive mass transfer, or we can call this as diffusion. So moving on to our another dimensional number, that is the Schmidt number, which is given by SC. Formula is nu upon dAB, or also can be given by mu upon rho by dAB. Here nu is the kinematic viscosity. Mu is the dynamic viscosity. Here rho is the density and dAB, as you already know, is the mass diffusivity or diffusion coefficient. So Schmidt number basically tells us the relation between momentum diffusion and mass diffusion. As you might have already guessed, it's very similar to Prandtl number. So now we will come to the actual correlation part. So first up we have the Gilliland-Sherwood correlation. This relation is basically given by Sherwood number is equal to 1.17, Reynolds number, Schmidt number to the power 0.586. This number is basically applicable for packed beds and turbulent system. As usual, like all the other formulas we have already talked about, this is also empirically derived from hundreds of experiments on packed bed. This number basically works for turbulent flow and very high Reynolds number. So Reynolds number must be very high and Schmidt number should also be very high. This relation is basically used in our gas absorption towers, the catalytic bed and trickle bed reactors. This is a very simple and it has a very good accuracy for this equation, but it's very geometry dependent and it cannot be applied for flat plates or pipes. So next up, another relation we will talk about is the Linton-Sherwood correlation. Okay, so this is given by Sherwood is equal to E into I to the power B SC to the power C. So this is a kind of very vague formula. As you can see, there is a A, there is a B, there is a C. These three are all empirical constants. These change with system geometry, changes from if it is a sphere, drop or film. It depends on where the flow is laminar or turbulent and if the flow is basically gas liquid or solid liquid. So this is applicable for fluidized beds, bubble columns, spray dryers. And depending on the system, you can customize this ABC and you will get a correct correlation. And for this, you basically refer to multiple books which are available. So from there, you can find the A, B, and C. So last up, we have Chilton-Colburn analogy. This is the most widely used analogy in mass transfer, as you can relate both mass transfer and heat transfer. As from this, we can find out the J factor, which is given by Sherwood upon Reynolds into 1 to 3. This formula is applicable for mass transfer, and if I were to write this for heat transfer, this will be given by Nusselt upon Reynolds into Prandtl to the power 1 by 3. And this formula for turbulent condition is basically equal for all. JD is equal to J is equal to J. This formula can measure heat or momentum transfer and you can estimate the mass transfer. This formula is applicable in turbulent pipe flow, in cooling towers, and in air-water contactors. So, it not only works for turbulent, high Reynolds number system, but also valid in laminar or low velocity flows. And this formula brings together both heat transfer and mass transfer. So guys, I hope that you have enjoyed this part of our engineering correlation. I have tried to explain you all the engineering correlation from friction factor, heat transfer to mass transfer in detail, as well as I have tried to kept it short as well to keep the video interesting. I
Yes,
hope
it was indeed very interesting. I understood most of the concept that was covered. Thank you.